Hello and welcome. Today I want to present you the AntTestTool. It is used to investigate the inversion, ring formation and randomness of different extensions of the Langton's Ant algorithm on multidimensional tori for the creation of Langton's Ant-based crypto systems. Let's begin with an overview of the content. First I will introduce myself and give you a short introduction about Langton's Ant and multidimensional tori. Then we need to define a little bit of vocabulary that's important to avoid misunderstanding. Then we get an overview of all models that are included inside of the AntTestTool, and we will investigate the source code in the deep to really understand those models. Then I will demonstrate you where you can get the AntTestTool, how to use it, for what to use, and how to combine it with the Nist-Statistical-Test-Suite. In the end, we will talk about the results, and I will give a short look out with some recommendations for the future. My name is Jonas Lummerzheim and I'm a master's student in computer engineering at the Technical University of Cologne in Germany, especially at the Faculty of Information Media and Electrical Engineering. I'm interested in artificial life and fractals over years, and I'm happy to combine that knowledge into this great project. Langton's Ant was discovered 1986 by the theoretical biologist Christopher Langton. It is based on a 2D infinite memory consisting only of zeros and/or ones and a step function which is based on the three subroutines rotate, recolor and forward. Rotate rotates the read-write head 90 degrees to the right or to the left depending on the color it is staying on at the moment. Recolor recolors the memory cell which is under the read-write head at the moment, and this is based on the color set. Let's assume we have a color set consisting of 3 colors, for example. While we can decide for each color itself if we want to turn right or turn left in this case. And then we have to use the recolor function on it. So let's assume we are staying on color 1, we use recolor, now we are in color 2. We are on color 2, use recolor, we are in color 3. And if we use recolor on color 3, we are again in color 1. Then we have the forward subroutine, while this is just a movement one position forward of the read-write head. If we want to use Langton's Ant in a practical way, we got one problem, since I'm pretty sure we have no infinitely large memories. So let's take a square. But a square got another problem, it has borders. And if our read-write head just crosses these borders, well, our program will crash. We can just apply maybe a rule. So we can say if we would cross the border, we just rotating the read-write head by 180 degrees and moving one step forward, and then we cannot leave the memory anymore. But, well, we have no memory cells where our head needs to act differently. And we just want that every memory cell acts in the exact same way. Well, it's just depending on the color in the memory cell. So how we solve this? Well, the best idea I could find was just the torus. And a torus can be very simply created by taking a square and lifting this two-dimensional object or presenting it in the three-dimensional room. And well, we think like about a piece of paper, and we can bend this paper now in a way that we create a tube. And when we created the tube, we can bend this tube again and create now a torus. Well, a torus is very nice since we can be at the outside of the torus or the inside of the torus. We can move at any position infinitely long in every direction we want. So we kind of solved our problem. But we got another thing here. We have later models which act on higher dimensional memories, and therefore we need a rule we can also apply in higher dimensional memories. And that's funny since a torus does exactly that. So we can just construct a torus from a cube. By this we are just connecting opposite borders, where now borders are not lines but squares. And well, now we can move in all 6 directions of a 3-dimensional cube, for example, infinitely long. Well, the same happens if we do it with a 4-dimensional tesseract or any dimensional hypercube you want to use. Let's define a little bit of vocabulary, since here are some terms used that are misleading maybe a little bit. So you know maybe ring from something like cryptography, or you know maybe a bridge from graph theory and so on. And well, I mean here at this point something different. We have here the ring. While the ring is something like the topology of some states that are correlated to each other. So you're able to reach each element of the ring from each element of the ring. But you can only leave one state of the ring in a certain direction. So you always know where is the front direction from this state and where's the back direction from this state. Well, you can think about the ant doing a forward step, or maybe if you invert it, it can do a backward step. So there is a particular important thing about this ring. You can only enter it and then stay inside the ring. You will never leave it again. So if we now have a look at the lasso, we can see that there are some additional states which have a forward and backward direction. But we're only able to go inside the ring from an outside state and never leave the ring and get again, for example, here to the state E or F. While if we find a lasso, we could just imagine that we see here only a lasso in the forward direction. There is another lasso connected to that lasso in a backward direction. And if we look at this both lassos together, we can see two rings which are connected now by a bridge. While it's here very important to understand that if we start on a bridge, we can go to the ring, but if we are starting in a ring, we will never come to the bridge again or come to another ring or something like this. Well, we have something more which we need to know, since this tool is working in a particular way. So if we want to detect a ring, we are just saving the memory at the moment. We are not looking at the states. And we just do a step, and then we compare the initial memory with the actual memory. And if we find that after a special number of steps, we find a memory where it's exactly the same than the initial memory, we say we have detected a ring. Well, in fact, that must not be a complete ring. It can be a part of a ring. But I noticed that if you find a value that comes again, so you have the memory state of the start, it's occurring again after, for example, 20 steps or something like this, then you know that the same state will occur after another 20 steps. And a multiple of the detected ring size of the AntTest tool will be the real ring size, which I mean at this point here. Well, that's just important to know, so that if the AntTest tool detects a ring, it's a part of a ring, but if it detects a lasso, you can be pretty sure that this is a lasso. And it was found that this will happen after a few steps. So normally you can think if the memory has lassos and you take a very huge memory, then it can be that you take up to maybe 80 steps or something like this until you reach a ring. But it was never seen that you need, for example, 10,000 steps or something like this. There was never seen a step number higher than 100 to find a lasso. At the left, we can see an UML class diagram of the AntTest tool, and at the right, we can see all included models. The AntTest tool is written in Scala, and therefore here are some terms inside of the UML class diagram which are maybe not familiar for you. So we can just see here that we have something like an object, and an object is nothing else than an implementation of the singleton design pattern. We have here a trait, and this trait is used just as an interface or an abstract class. And we have here the function f out, which is just a variable, which is a function. So you can just place there another function, which just provides another possibilities, for example, for printing, exporting, or something like this, if you want to plug in there another function for that. Model is here used in a special way. So it is used for the design pattern of a gateway. And we have one model inside of the control object where we can place there any model we want. So we can place there AntTestTool, for example, or any other. And then we have the possibility to use every function we can see inside of the test object. So every test function is implemented in a way that it can be used with every model implemented here. And this is enabled by using the design pattern gateway with the model. Every model must implement the following functions. First we have write, while write is just used to place some information in the memory. Then we have the step function. I guess you already know what that means and what it does. We have here the read function, while read is just the opposite of write, while we are here getting out the memory of the model, and we can just work then with the memory as an array. And we have here print, while print is just used to display the whole state of the ant, including the read-write head, the direction it's facing, and the whole state of the memory. And we have then a function set parameter, which is just used for adding some additional information if needed. For example, we have AntTestTool, where we just need to add those information, and therefore we use the set parameter function, which is just flexible, so you can just place there any size of int array you want. And we have then the reset function, while reset just resets the whole state of the ant, but not the memory. And you can think about that the position is then reset to 0, 0, or in higher dimensional spaces, for example, 0, 0, 0, or something like this. So a position that's only consisting zeros. And we have then here an invert ant function, while the invert ant function is used to, for example, rotate the ant or just invert the behavior of the ant, that you can say if you have gone 10 steps forward, you are now inverting the ant. If you know going again 10 steps, now you have the initial memory state again reached. Well, and in the end we have some models which are not implementing every function. For that we have here the isInvertible function. If we not implemented the invert ant function, we can tell the test functions over this to skip this test. Let's begin with the models. First we can see here AntTestTool, which is just the basic implementation of Langton's ant on a two-dimensional torus of any size. So we have here the extension AntTestTool, which now allows us to define a variable color set, because AntTestTool only has two colors, where you have one color where you turn to the right and one color where you turn to the left, where you can define here as many colors you want, but you have to define for every color if you want to turn left for that color or to the right. Then we have here AntTestTool, which just use discrete convolution, which means that we have here in history memory where we're just placing all the values we have met, for example, in the last 3 steps. And in addition, we have the value where we're standing on at the moment. Now we are summing up all these values, and we're taking now modulo 2 of this, and then we get a 0 or 1, and with this we can decide if we want to go to the left or we want to go to the right. Here it's important to note that you understand that AntTestTool and AntTestTool are invertible, and AntTestTool is not invertible in all cases. So just imagine you have memory which is full of zeros, and you have a history memory which is full of zeros. That cannot be. You cannot come to the all zero memory if you not have met before, in the last step, a 1. So I've decided not to implement here the inversion, because I'm assuming that this is not working in all cases, and I don't understand in particular how I can decide if a state is valid or a state is not valid. Now we have the ANT3D model, which works like the ANT2D model, but works here in the three-dimensional space. For that, we need a memory that can contain 4 different values or colors. And if we have there a 0 in the memory, then we are turning up. If we have there a 1 in the memory, we are turning to the right. If we have a 2 in the memory, we are turning down. And if we have a 3 in the memory, we turn to the left. So here's something very interesting. So the inversion of this model works in another way than it does for ANT2D or ANT2D-MC. So inversion at ANT2D is done using the read-write head and rotating it by 180 degrees, then moving it 1 position forward, and then the normal step function can be used to just undo all steps done until now. Then we have the ANT2D-MC model, where we just need to permute the color set, and then we can do the inversion there on the same way. And for ANT3D, we're doing it in another way. So we have here an inverted version of the turn function, and we switching between these functions, so we can go forward and backward in this case. To give there a nice idea how this really works, you can think about in case of ANT2D, you are just moving forward, you're rotating by 180 degrees, and you are again moving forward. So while ANT3D just moves forward, then uses invert, and that makes just that our model now works backward. So it does not forward steps, now it does backward steps and goes backward everything it does before. And so now everything is done in another way. Then we have the ANT model, which is just like the idea of the ANT3D model, but for any dimensional space you want to use. So we have here the way that you're defining just the number of dimensions and the size per dimension you want to use. And then this model will act on this like ANT3D acts on 3 dimensions. For example, ANT would need 6 colors on a 4-dimensional memory. Well, about how it works, I would like to talk a little bit later, because here it's complicated a little bit. It's just easy steps, but there are some steps, and we have here the stim ring with a direction, and we are not doing everything in a correct mathematical way. We have here a very simplified function which decides for us in which direction we are facing at the moment. AntConf behaves to ANT like ANT2DConf behaves to ANT2D. So here the only difference is that we have here not modulo 2, but we use here modulo the size of the color set. Last but not least, we have the fractal ANT. While fractal ANT is an extension of ANT, so it works on arbitrary multidimensional tori, and it's based on a depth, while depth tells us how much hierarchical levels there are. So for example, 3 hierarchical levels are 2, 4 hierarchical levels would be a depth of 3. And well, we have a queen, while the queen is the master of all, and it has some children. So the queen got this children, the children got grandchildren, and so on, depending on the depth. And we are splitting up now the dimensions. For that, we must be sure that the dimensions equal our depth plus 1 times our subdimensions. For example, if we have the memory with a dimension of 9, we can now set, for example, depth 2 and subdimension 3. So every fractal ANT inside this colony will have its own memory, which has then 3 dimensions, while the memory of the upper ANT kind of represents all its children. So the first memory cell of a children is now used for the fractal parent in this case. Well, I'll talk about this more in detail when I show the code. But here is just important that you note this relation between subdimensions, depth, and the dimensions. The basic construction idea here is taken from the Menger sponge, which was introduced 1926 by Carl Menger. I just noticed I have two little bugs inside of my UML class diagram where you can see backward on ANT3D is a function which returns unit, and you can see that ANT2D has setParameter, which is an implementation of setParameter of model, and thereby it must return unit. Now it's time to start with the code and demo, so I'll now switch to my Scala IDE. At the left you can see the AntTestTool. The Scala library container 2.12.3 is used and Java 1.8. Now we have a deeper look into Ant, fractal Ant and the tests. So here we have Ant. And well, it's working on any arbitrary multidimensional tori. And for that we need to understand how it can decide in which direction it's facing and how it's oriented in the multidimensional room. So maybe first just imagine you're in the three-dimensional room, and in the three-dimensional room, if you know that, for example, the front direction is north and you know the up direction points to the sky, then you always know that right of you must be east. And we are using here now a little bit different system. So we have now here the dim ring, while the dim ring is a ring or an array where all dimensions in. And you can permute this ring, and the 0 index of this ring represents now the direction you are facing, and all other dimensions in this array tell us how we are rotated or oriented in this multidimensional space. So we just get from the dim ring the axis, and then we know in which direction of this axis we are facing. So maybe we are facing in the positive or in the negative direction, and therefore we have here the direction variable. So let's expand this window a little bit, because I just want to show you 3 functions and I want to show you all of them at the same time if possible. So here we are. All 3 functions are used to permute the dim ring. So first we have here a shift dim ring function, which is used to shift this ring to the left. A special number of steps, so you can define how far you want shifted, and remember it's a ring, so there will never be an element which is deleted. So it's really like if you have a ring you're placing on the desk, you have all your dimensions on this ring and you're just rotating this ring. Then we have here the update dim ring function, while this is used just to place a special index at index 0. And all others are then filled in the remaining order of the old dim ring. Then we have here the invert dim ring function, which does just invert the whole order of the ring. And now an interesting thing is that we can, for example, combine shift dim ring and invert dim ring to invert the order of the ring, but still hold the element which was at index 0 before we inverted the dim ring, now again at index 0 of this dim ring. So here we have the next interesting function. It's called position to index, and it is used to translate our position, which is based on the number of dimensions we have, and calculates from it an index to our memory. And our memory is just a simple normal array holding some integer values. So we don't need any multidimensional array or something like this. Here is a very, very simple way. We are just computing everything in a multidimensional logic and translating it then to our simple index. So let's skip recolor. I think you already know what it does. And we have here the turn function, while turn works here in a special way. So think about the number of symbols which can occur in the memory. And this is exactly the number of dimensions in which we can change, and then the number of directions we can change on this dimension. So we have to multiply this. So it's the number of dimensions we can change times 2. And well, we are working on the dim ring. So if we just note that we have a value which is bigger than the actual number of possible dimensions we could switch to, then we are reducing this to a valid value. And by that, we then know that we have to switch the direction. So we are just multiplying the direction which can 1 or -1 by -1 to flip it. Well, and then simply just do an update of the dim ring with the index of the, or with the dimension found at the index, which is represented by our found symbol. And then if we have to invert it, we are not only doing this to the direction, so we're doing it in addition to the dim ring, where we just inverting the whole order of the dim ring, but we stay with the index 0 still on index 0. So then we have here some more functions. Let's have a look at these. So we have here first 2 modulo operations. It's just mod dimension, and we have mod size. And well, I just noticed that in Scala, if you use a modulo operation on a negative value, that this will not work. And thereby I have here just a simple recursive implementation which fixes this problem. Then we have just the forward operation and the right operation, but I think you already know what those do. Now here the step function can be seen. It's important to note that not only the functions used by step are inverted, but the order too. So we can see here we are just doing for a forward step the operations turn, recolor and forward. And for a backward step, we do backward, inverted recolor and inverted turn. So this is the inverted order of a forward step. So let's go over some functions very fast. So I think you already know what read does. You can imagine what print does. Set parameter is here not used since here's no additional information needed. Then we have here the reset function, while reset just resets the state of the read-write head and resets here this inverted variable, which is used to decide if the model has to do a forward or a backward step. Then we have here just a way or a function which is used to make this inversion, and we can just here, this is just based on this variable where we just take it to true if it's now walking backwards. Then we have here the inverted recolor function, while inverted recolor does here just the same like recolor, but it shifts this colors into another direction. Then it's done by a forward step. So in a forward step, you would recolor color 0 to color 1, and here you are just doing the opposite. So you would recolor color 1 to color 0. Here we can see the inverted version of the turn function. And well, it's just important that you note that we have here an inverted order of the operations shift dim ring, invert dim ring, and update dim ring. And we are using here the shift dim ring operation with another index, which allows us to invert the operation we did just in a forward step. And we have here another update dim ring function called inverted update dim ring. And this does just the inverted action done by update dim ring. So this function can be seen here. So it took me some time to understand that this update dim ring function is invertible, but it's just very simple. So we are just taking the index 0 we have now at the index which we can calculate using the symbol which we find where we actually staying on. So we just place it there, and then we just shift everything which is at the index we have placed that and before that index, and shift that one position to the left. And then we have just inverted our update dim ring function. Last but not least, we have here the backward function, which is just an inverted version of forward. And the only difference here is that we use in backward minus direction, while we are using in the forward version plus direction. Let's have a look at fractal ANT. So we can see here fractal ANT is just an extension of ANT, so everything is available from ANT. And we have here in addition the children, and the children are very near related to the memory, since, well, it's not the optimal way like it's done here, but it was a problem just to debug this and to make this proper working, because we have here very huge memories where this gets interesting. So the number of children is equal to the number of memory cells of the current fractal ANT, if it has children. So you can think that you will not have children if you're in the lowest hierarchical level, and only if you're in the lowest hierarchical level, then there is the real memory. So only the lowest hierarchical level contains the data we really working on. And every other memories we have here are just kind of a help at the moment to simplify our solution. So if you are not in the lowest hierarchical level, then you have to calculate your memory. And well, here is a memory, the representation of the first indexes of all childs. So you can think about of the first memory cell you have, then you look in the memory of your first child, and there you look at the first memory cell, and now you know the value of your own memory cell. So if there's a 1, you have in your first index also a 1. And we are updating this from the lowest hierarchical level up to the highest always, so that we are sure that we have at the moments where we're calculating important information, always the correct information at the moment that is really in the physical memory at this point. Now let's have a look at depth. Well, depth here is a little bit more complex than just mentioned in the overview, because the depth of the overview you can just use if you want to use the AntTestTool and enter it, and it will work. But you have here that depth represents the layer in which the actual fractal ANT is in. So the value we calculated is just correct for the queen of the whole colony, and then the hierarchical level under the queen will decrease the depth by 1, and the grandchildren will do this again, and so on. So that we have then a lowest hierarchical level which has exactly as many memory cells how we defined with the dimension and size. So for that we cannot use any more dimension, but we have here something called subdimension. So think about the subdimension like the dimension of only one fractal ANT in the whole colony. To get now the same memory size, whole memory size, like we get when we use ANT with the same number of dimensions and size, we are just dividing our dimensions. So we can think about we have number of layers, and number of layers times the subdimensions must be equal to the number of dimensions. So let's go through the functions. we can first see here we have shift dim ring, update dim ring, and invert dim ring, and the only changes I made here are that we have now subdimension instead of dimension. Then we can see here the two very important functions recolor and recolor all. So let's assume you have a fractal ant which is in a higher hierarchy, so it has children and maybe grandchildren and so on. Let's assume we are the queen, for example, and we make a step and we need to recolor our memory. But what do we then? So we are also recoloring our children. So we are recoloring, in this case, only the child that corresponds to the memory cell we are recoloring, but we recolor it complete. So we recolor every memory cell of this ant. And we are not only recoloring this ant, so we also recolor every child of the child. So all grandchildren will be also recolored, and the grandchildren, and so on, until we are in the lowest hierarchical level. Then we have here some more functions. We have turn, position to index, and mod D, where here again the only difference is that we are now using subdimension instead of dimension. Here we have the very important function write, which does not only write something in the memory, so here this function constructs a whole colony in addition. Then we have here the read function, where the read function here does some more than a normal read function. So here the complete memory is assembled and we get then a normal array which is built up from the memories of all ants of the lowest hierarchical level. So print is not really interesting. We have then here the step function, where this is very important because the step function is here recursive. So we are doing first a step by our own, and then we doing a step on all children of that ant. And then inside of the step function of that child, we are calling again all the children to step, while only the lowest hierarchical level does not call its children to step. And here the important thing is that we then update the memory, but here the update of the memory will happen first in the lower hierarchical levels and after that in the next higher levels. Well, here is very important that if we want to invert this, we have not to invert the whole order. So we invert the order that we are calling on the children, and we are calling our self step function as the last here, but we are updating the memory after we calling steps, since otherwise our update of the memory function will not work in this recursive way. So let's rush through the last functions. So we can see here set parameter. It's just used to set depth and subdimension in this case, because this are variables which are not used by other models. And we have now here the reset function. Well, if you call it on the queen, it will call it on all children and so on. And that means if we reset the queen, we reset the whole colony. Then we have here the invert ant function, where here's the same like for reset, where if you call it on the queen, the whole colony will be inverted. And then we have here just an inverted version of recolor and inverted version of recolor all. Well, that's, I think, very simple to understand from now on. And we have then here an inverted turn version. We have here inverted update dim ring. And so the main switches here again, the order of the functions, and we're using in parts inverted versions of functions. And we use here subdimension instead of dimension. So now let's have a short look on the test functions. So this will be very simple, I think. Let's begin with the test 0. We have here just our model, then we initialize the memory only with zeros. We do a defined number of steps, which is here called cycles. And after that, we are just printing the memory. Here we can see test random ring, where we here initialize our memory with random values, which we pick that they are really random. So if we can have big color sets, then the random values will adapt to this. Now we are just saving the initial memory state, and then we are doing a step. And when we do a step, we compare after the step the memory with the initial memory, and if both are equal, we know we found the part of a ring or we found a ring. But there are some cases where we are not finding a ring. So it can happen when we have very, very large memory so that we cannot do enough steps in enough time. So we have here just a step limit of 1 million steps. And well, we should take small memories for this to get good solutions. So if we use a model which can produce some lassos, for example, it can happen that we run this function and we could run it infinite long and it would never find the initial memory again. But if we now take another memory, so we are just replacing our initial memory with the memory state after exactly 1 million steps, and then we are going on resetting our step number and counting now when we find again the same memory, and then it can happen that we, for example, find a very low number, something like, for example, 32 steps. So if this is not working, we are just doing this again. And if we then find no cycle, then we just say we are out of range and we cannot calculate any solution that helps us at the moment. So because fractal AND does multiple steps in each step, you should not do so many steps here. So if you have a very big fractal AND, this test run can be very time consuming. So I just decided here to make the step limit a little bit lower. And in addition, if you want to use this in debug mode, well, then there is so much information printed that we not do that many steps. So you are just doing this to find bugs, for example. So let's have a look at create test file. This function is just used for the Nist-Statistical-Test-Suite. We are initializing our memory with a random value. Then we are doing a fixed number of steps. After the fixed number of steps, we are just going to export our memory, and we're doing that so often like we define with the variable lines. And well, then we are calculating the sequence length, and you can think about lines like it's the number of sequences, and we need both values for the Nist-Statistical-Test-Suite. So if you use this tool, this will be displayed for you. So now we have here test random invert AND. We have here again the variable cycles. So we are initializing here our memory in a random way. Then we do a cycles number of steps. And then we are inverting the model. We do again the same number of steps. And if we have now the same memory as we had as an initial memory, we know that the inversion worked. Then we have here test zero invert. It's kind of like test random invert, and you can think about it like we are just here initializing the memory with only zero values and comparing if the memory at the end is also all zero. Finally, let's have a look at test full. So test full is just used to do the tests multiple times, and we can just define it by loops how often we want to do this. So we have here two tests that are used. Test random ring is used one time, and after that we are just doing test random invert, and that we are just doing 5 times, and we're doing it first with 10 steps, and then we're just multiplying the number of steps in each next try by a factor of 10. So if for this model the invert function or a backward step or something like that is not implemented, so here the test random invert ANT will not be performed. So let's start and just have a look how we can get all the things we need. So here is the GitHub page. You will find the link under the video when I publish this, and then this will be public as well. So you just go here and you can download it, or you can clone it and whatever you want to do with this. So I'm just downloading it here as a zip. And then I have a look here, what do we need else? So I've just prepared Java is already installed. So here's nothing more I need to do. So I'm just showing you where you get all the stuff you maybe need. And you have here the Scala IDE, and well, it's just an extension of Eclipse, and well, I think working with this was very nice, so you can try this. Then we have SBT. While SBT is an open source build tool for Scala especially, so it's used in some other languages too, I think, but well, it's well known in the whole Scala community, I guess. So, and finally we got here the Nist-Statistical-Test-Suite. If you want to have a look at the randomness or pseudo-randomness of all these models, then you need this in addition. So the idea is you have here this download. We're loading this here. Well, so you can just see I'm downloading it here. Well, I've done it before just to show you or to make sure that this is working. So we can see here it needs some more seconds. And well, we have first here the AntTestTool. Give it, okay, it's done, I think. So we're just copying the STS and the AntTestTool, and we're placing it in a folder where we want to have it. So I will just change here to my test folder, copy it there, and then I will unpack this. We have it. So it's the first, and we are unpacking the second. Well, it's done, and now I will just delete this, and I will just remove this ugly one here. So, well, here we got it placed. Now it's very important that we have to do something with our statistical test suite, since we can have a look inside of it. And we have here a make file, and we have here just source files. So we have to compile this. And well, for that you need to have maybe some installations, and what's very important that you have the make command run. So normally this is not available, and well, I have Cycwin here installed, and I have a compiler, and I have a running make command. So I just want to show you now, if you have all this running, how you can now compile the Nist-Statistical-Test-Suite on Windows. So I'm just changing here the folder, going to the test folder. Now I have just to go here, and I know there are some more subfolders in it with all the same name. And we'll have a look in this, and this looks nice. So I just want to show you now how this works. So it's very simple. We are just going here and typing make F, and we have then here just the file we see, so it's just make file. And well, if it's properly working, then you should see something like that. This will work very fast. So here we are finished, and now the Nist-Statistical-Test-Suite should be usable. But we don't need this at the moment, so I just would like to launch another CMD window, and will first show you how the AntTestTool works, but later we will need this window here. And what's just important to note, we can now have a look here, and we see we have now this SS-exe. So this is a really important file, so we know if the file is here, you should be able to use it, and then everything should be fine. So at the moment we are here, and I will use this window. So I have again here to change the location. Then I have to go to the AntTestTool. I think here's another folder inside of it again with the same name. We have a look if we are in the right location. So what's here important, we can see we have here this build.sbt, and that this file will do all we need. And we are just typing in the moment sbt run, and this will do absolutely everything for us. So give it a moment. Well, this can take, if you run it first time, up to 20 seconds, I think, because here again, it's now compiling and preparing, creating scripts and something else. So, but it will do it all on its own, and you don't have to configure here anything. So it's really, really simple. So let's have a look at the main menu, and you can see here first you can decide if you want to activate the logging, but you only need it if you want to export the log. So at the moment I'm not interested in this, so I would like to use here deactivate logging. And just that you know, if you activate debug, you have activated logging, and you have in addition very, very much print comments everywhere. So this will really slow down the tool. So I'm just deactivating logging at the moment, and then we have here to choose a dimension. And so I would just like to start with showing you some interesting things about the rings here constructed and what I really mean with this. And for that we are taking a really small model. So we take here dimension 2, and we say it has a size per dimension of 3. So this memory will be 3 times 3 memory cells. And we're starting here with the classical Langton's ANT. And just remember, the memory we are using here is the torus. So you're here not on a normal square, like think about a donut. Well, here we can see now all our test functions. So export log we will not need. But I think with test 0 we can have now a little bit more fun. So if we want to use test 0, we are just typing here 2, and now we have to enter the number of cycles we want to do. So first we can just start with 0, so we can see what happens if we just type an enter without anything in. So I'm just redoing this here. Well, it's interesting. So my tool, if you do something wrong and you type something that's not the correct way, like you're typing nothing and you're hitting, like me, 2 times enter without typing anything, then this can crash. So I'm just doing the same like before. I'm just choosing here the ANT2D model, doing now test 0, entering here 0, and you can see now here's my all 0 memory. So now to show you, well, I have here not the test implemented, which can calculate the ring size on an all 0 memory. It's always here on an all random memory, but I can say you that here would the tool detect on this memory, if it's randomly chosen all 0, then it would detect that this has a ring size of 22. So it's very simple. We can check this if we just type here 22. So it worked. And just that you see that this is not a totally not working tool, so it's really doing what it should. So we are just doing something else. It's not the ring size. So you can see here, well, it's permuting, or it's not permuting, it's changing the memory in a way that we could say just maybe it could be pseudorandom or something like this. Well, now the interesting thing what I want to show you is that this is not the really ring size. So it's very important now, if you want to find the real ring size, then you have to do additional steps. So we are starting now with have a look at how our memory looks after 2 steps. That's very important. So we can see here we have 2 ones in the first line. And now let's do the same thing after we have our part of a ring done. So after we see our initial value the first time again, and then 2 steps more. So we can see here, oh, that's different. Well, it's kind of looking like if we just shifted the whole memory 1 position up and the image is then just doing the same like before. Maybe that's true. But, well, if there's not the ring finished, so we can just think about what is with 42. Well, that's again all 0. Okay. And how it looks now, just make the cross check. Maybe it's really shifted. So let's try now 46. So, whoa, well, it's looking like it's shifted, but it's only true if we now do it again for 66. Let's do it. Oh, it's again. Well, that's very nice. And now if we do it again for 68, we need the initial picture we saw again. So we have here, whoa, it worked. And just to make sure that this is the initial one we had, we are just doing it again for 2 steps, and we can now see that here really a full ring is now done. So this is a whole ring, but our test random ring just detects the first again occurring of the initial memory. So now I'm just going through the other tests you can do here to demonstrate that you can use them. So we have here test random ring, and we can see it detected now a ring or a part of a ring with 70 steps. So it's randomly initialized. So we can say if we do this again and again and again, we get kind of every time a different number here. And well, then we have the next test, while it's now an inversion test. So we go with our model, for example, 1000 steps forward, while I think you understand that if we have those rings, any number about bigger than the ring size that could be possible in the real ring is not necessary. So we are repeating then the steps we already done, but to make sure we just move a long way, and then we move that long way backwards. And if we do this and we hit again the initial memory, then this works. And we can this do again for an all 0 memory. Let's do it this time for 100 steps, and we can see that this is working. So the next thing what's here very interesting is the test full. So here we can just say how often we want to do some tests, and there we're doing multiple tests, but those are all random based. So there are no all 0 tests in this idea. So I'm just saying we want to do the tests 10 times, and we can see it's doing, and it makes for us some results. So it counts things. So we can see here we have here only positive values. That means that we have here only rings detected. We can see how often we found a special ring size. And if we find here negative numbers, that means that we have a lasso detected. And if we find a 0, we know that the ring size was just out of range and could not be detected. So then we get here average ring size, average lasso size, and number of rings, lassos. out of range. And then we get our results for the inversion tests for 10, 100, 1000, 10,000 and 100,000 steps. Well, I think that's enough for this simple one, and I guess we should now change just to the next model. So I'm just closing this because you cannot switch the model during a run, so you choose it one time and then you can perform tests like you want. And we are just doing again here the sbt run command. Well, it takes some seconds maybe, and I think it's done. We're starting now here the deactivated logging again, or well, if you want, I can show you how you can log something with this and how it looks maybe. And we have here the dimension we could enter now, and the interesting thing I want to show you now is how we can make here something for the Nist-Statistical-Test-Suite. So I'm just picking here the dimension, and I would like to begin with the dimension what you want, 9 or 5. Let's take 9-dimensional memory. So that means that our number of different symbols that can occur in the memory will be not 18, it will be 16. So the trick here is you have to reduce the number of dimensions by 1 and then you multiply that value by 2. And here it's very important that you make this in a proper way so that you have a value at the end that is a power of 2. So 16 would be great here. And this is only needed if you want to create a test file for the Nist-Statistical-Test-Suite, since the Nist-Statistical-Test-Suite can only read zeros and ones. And we have here just our 16 different symbols, and the Nist-Statistical-Test-Suite cannot work with this. Thereby we are translating this, and the translation algorithm here is just based on the binary representation. So this will, I guess, work here. So we have now our 9-dimensional memory, and I'm just going here and say we take now a size of 3. Then we take the multidimensional ANT in this case, since we cannot use here the 2-dimensional model or 3-dimensional model. It's not working. But well, we have now here our multidimensional extension. We are using this, and we're just doing here, for example, we can do test 0 with 10, well, let's do 10,000 steps, and we get here an output, so you can understand that our memory is now kinda really huge. So I will now create here the test file. So I'm just going to create test file, and now I have to say how many sequences I want, and for the simple demonstration we are now just taking here 10 sequences. So it's now initializing the memory of the model in a random way, and then it does a special number of steps. Well, that will be a little bit bigger than the number of steps I have done, since you can see that here are really much zeros. And well, we're doing steps in the height that we can generate here pseudorandom data and then test if this is really pseudorandom. So we're just seeding here the ANT, and then this will generate for us other random values based off that random seed. You can think about this in that way. So we have now the little problem that this takes a little bit more time, since we have here really much data. And well, I will just cut here and come back in a minute or in 2, so make this not so boring. So we can see it has finished. Well, we got here 10 sequences, that's what we entered here, and we have now a sequence length. That's very nice. So what I just want to do now in the end is, well, I can show you the export log. There will nothing special be in, I think, in this case, but we can just use it and then we can finish. And you can think about that just some of the outputs we got are now in the log file. So we can go to the test tool and we have now here our log. Well, I like to show it more here. So we did only one test and the export function is not logged here. So it's just if you want to do several tests or you do a long full test run and you have the several data, then you can just export all the outputs you had and have a look later on it if you need it. So then we find here this test data point txt, and this is the file we have created to show you the values we got here, since I really think this should here look everywhere like random. And we see it's a very huge file. So we have here some lines. But you have to make sure that this file is really huge. If it's not huge enough, well, this is a kind of small file for the Nist-Statistical-Test-Suite. So there are kind of bigger files, I think, than we'd see here. So we are just copying this. And now we are going to the Nist-Statistical-Test-Suite. And we are entering... Well, we can place it just here. Here are just other test files prepared. And if you want to check if it's totally working, you can always check, for example, the data.py file. Well, I'm pasting. I'm not able to paste. I'm able to paste. So we have it here placed. And then we are just starting with our demonstration now, how we can use the statistical test suite. So what's very important is we have on the one hand, we have this window where we got our sequence length, because that's very important. And on the other hand, we find here now the test suite. And well, I've done here nothing, you know, this window from, well, some moments ago. And well, I've now just to use the SS axis. So we just type here SS and then we type here the number we have got there. And it works. So here we really have the sequence length, that's very important. And then we decide here to use an input file. And now we have to say where this file is, and we placed it in the data folder and it has the name test data.txt. So now it's important you can here just decide what you want to do. And if you want to do everything, here's written that you need to place here, well, enter a 0 if you do not want to play all of the tests, and else 1. So we are doing the 1. And we have here now to decide how we want to configure the tests. Well, I think the basic configuration should work in most cases, but you may have a look in some special in the test results and the corresponding folders and files to find some tips if you did something wrong. So if you find a value in the solution later, which is kind of not looking good, then have a first look in the folder and look in the test results files. If there's maybe written that you chose a block size too big or too small for a test, then this will not work properly. So we want here to do every test, and we are very fine with the standard configuration. So we want just to continue with a 0. Here we are asked how many bit streams. So here comes our number of sequences. So we have done 10. But I can just say you, if you have created more than 100 sequences, I just noticed that this will probably generate some errors I'm not able to fix properly. So it's just working for most tests, but some tests not so fine. So we are just entering here the 10. And we have here to say that we have in this case ASCII. So we just made a file where just zeros and ones inside, and which is configured in a way or concepted, or the syntax or form is in a way that this tool accepts it. And we can say now just here do this. So you can see now that the statistical testing here is in progress. This should go very fast. And well, we're just finished. So let's just have a look in the results. So for that, we're just going to our folder. We're going here. Then we have here the experiments folder. Then we have algorithm testing. And here we got a final analysis report. Well, and here we can see the solution. And what's very important, just if you're no professional guy who works every day with this and you want to use it anyway, it's very simple. So we got here our proportion, and we can go here downwards and then have here look. And here is just written, if we have a value that's lesser than 8 here anywhere, then we know that there was something that's not passed. And we can just note that every value here is higher than 8. Here's not 1, 8, I think. And thereby we can just say that we have here clearly defined pseudorandomness. So I think, well, that's very simple, and I hope you can work with this if you have to use it. Well, maybe I said this in a little bit confusing way. So the Nist-Statistical-Test-Suite, if you pass all tests in the suite, this not means that it must be pseudorandom, but you can be sure if not all tests passed in a flawless way, then you can pretty sure that it is not a matter of pseudorandomness. If you say that's not enough information for you, I can just show you here are folders, and there are again results and stats inside, so you can just have a look in this and can see the detailed test results on any test. And we have here such p-values which are just later used to calculate if you pass the test or if we not pass the test here. So, but if you're interested in this, I think you have to do it on your own. I will not show here more of this. So I think I showed you most things interesting, and the only thing I want to show you now is how you have to configure the tool if you really want to use a fractal and to show you how that could look. So to do this, we are going just here for the SBT tool again, SBT run. So we have here done again our AntTestTool running, and we are now using the fractal ant. That means that we have here to choose a very, very big number of dimensions. So I'm choosing a very small size, very high number of dimensions. We're choosing the fractal ant, and we are now just splitting our 16 dimensions into 4 hierarchical levels, which are based each on again then a 4-dimensional subspace. So we are just saying here 3, that stays for the 4 hierarchical levels. Then we have here 4, which is meant for the subdimension. And then we are here. So the very interesting thing is just if we say now, let's do one step on this ant, and you can see here, so it's recoloring the whole memory far more often than any other ant. So one step here is one step of the whole colony, and well, therefore we don't need that many steps. So what we can do here is we are just doing, for example, let's do 100 steps. And we can see here we got a very, very nice kind of random pattern. It's looks really like random at the moment, I would guess. Well, maybe we need some more steps or something like this. To see here random in is very, very hard, and you should cross-check it always with the statistical test suite. So, well, that's what I wanted to show you. And well, I guess I want to show you something more than this, because we can invert this. And it's very fascinating because I just noticed the bug that I had over 1 month in this, and I couldn't debug because I didn't see it. And I noticed it while I produced this video, and now it's really working. I'm so happy that's now working well. That makes some of my test results not really valuable, but I think I'm happy anyway. So that's a good thing that's now debugged. So I'm just going out of this, and there's one additional thing I want to show you, because we just didn't saw it until now. We can detect lassos, and for that I will just choose in this case a very, very small two-dimensional memory again, and then I will show you that I found that all convolutional models will just produce those lassos and not only those rings, so that you see that these tests will make sense in any way. So not every model does this properly, or well, at least it's when it's implemented in the correct way. So we are just entering here a number of dimensions 2. We're entering a size, let's say again 3, and we're choosing this time the convolutional two-dimensional ANT. And well, we say it has an history memory, and we give it, for example, history memory of 4, and we say we have there only zeros placed. And now we can go and just say we make here some ring tests, for example. So let's do the test ring cycle count. So we got, oh, it's no ring is found, it's now a lasso detected. So that means that the start state was not found after 1 million steps on this very, very small memory. So we can just check, well, we cannot check if the inversion works here since I didn't implement the inversion, but you can clearly see here that it was detected that we cannot invert this model in all cases. Well, we have to see which states in the convolutional history memory are acceptable and which are not acceptable here. So I think now the demonstration of the test tool and the test suite and so on, that's done, and we're going back to our PowerPoint presentation. So we can see here we have the results. Well, I've done it really brief in a small way, so I'm not showing you here all my result tables and things I looked at. So maybe one interesting thing that I'm not showing here in my results is that you have always, if you use an 2x2 memory, every model creates a ring on size 8. And well, in addition, we have here just an ordering of the models. So we can see here first we have our ANT model. I think it's very suitable as a PIG at the moment. If you choose a high dimension, so you have, well, I think there is a chance if you use the normal ANT and you have a really, really bad pattern in the memory, you can create very, very small cycles, and there's no guarantee that you will have there a pseudo-random thing in the memory. But well, I tested all models with kind of 5 seeds, and all showed pseudo-random behavior. So we can just see at this that there were all memory cells visited. There is no memory cell static, for example. So this should be detected if we have here a non-random pattern, so that there are static bits in it. And well, we have here first the ANT, why we use here higher dimensions, and thereby we have more symbols, and we must visit every symbol several times to complete the ring, and we are changing maybe in completely different directions in our multidimensional room. So I think just the chance to find any pattern in the memory that really creates a movement of the ANT, that it's not visiting every memory cell, is here kind of zero. It's never happening with ANT. So I think it's very suitable. Well, we cannot parallelize it, so it's kind of going slow. So it's going step for step for step for step, and you cannot split it on several cores or something like this. So then we have here the discrete convolution models, where I can say, well, we have here found lusses and rings. That means, on the other hand, that the rings we find must be smaller, or there must be a less number of rings. And well, that's not good in the sense of a pseudorandom generator. So you want as many random numbers you can generate with one seed as possible. And so we can say discrete convolution is here not really target oriented. So then I have noticed that when you're using multicolor sets and you choose them in a good way, so you can choose really bad color sets and this will totally not work. For example, if you choose only zeros in the color set, well, you're always turning left. That means you're always on the four memory cells and will never leave them. So that's really bad. But if you really choose a very, very nice pattern, you can increase thereby the ring sizes which are produced. Well, you're not visiting the memory cells so fast, so you're kind of making in some parts, depending on what you configured here, maybe more movements that are hitting the same memory cell often and then changing to other memory cells and recolor them. So fractal and, well, I didn't really test the really final implementation. I did previously some tests and, well, at least with the bug, the models that just created rings were absolutely usable as a PAG as well. But I think now the pattern is very, very much better. So the problem was that there was a little bug that just the second, not the bottom layer, but the layer above it didn't do his step function. So I just had there a problem with a limit condition. And well, now it's probably working, but I can just say that fractal AND is not so massively tested, but I think it's now producing on any torus you can create here where you find a valid configuration, then it's really working and it's invertible in all cases. Yeah, I think we have here enough talked about the results. Let's have a look at the lookout. So there's one little problem with ANT, so you cannot really use it as a block cipher since, well, you cannot define as many keys you would like to make it secure. We cannot generate here really working keys of a length of 128 bit or maybe bigger, and we need something more we can configure on it to give a possibility to define keys that are secure. And I think a very, very good idea is just to combine ANT with the ANT2D MC model. So we are just adding here to our multidimensional solution a way where we can define the colors we're using. That would, I think, really increase the usage possibilities of ANT, where we are then maybe not only able to use it as a block cipher, so we can maybe build a hash function of it. So I think you could reset several times the read-write head position, so you're not able to undo this. You cannot go backward then. There's absolutely no way. In the possibility that you maybe reset the position 80 times and always the same position is the initial position is also always there, I think that will not happen. But well, we have to check for a hash function that there is for at least if we just take the period which is here defined as a part of a ring, that in this period no memory is shown twice, so that we really can say that there are no two values that are the same. So we could just plug in every different file and no two files could produce here the same hash value. So we have to check here more. So that's not so easy. And well, it's for sure you can use, if you choose the color set in a good way, you can then truly use it as a PAG, like you can use ANT at the moment perfectly. Well, then we have fractal AND, where I think fractal AND, the greatest thing on it is just that you can, in parts, I think, parallelize it. So you could just place, for example, any AND on a different core, and the only communication you need is just to say, very simple, you have only maybe say recolor all. You just given one, you say it's just a comment, no, recolor all, that's one comment we need. And the other thing we maybe need is just to update the memory upwards. So there we have another communication which must take place, so that we now say if we updated something which is relevant to our first memory bit, then we have to tell our parent that our first memory bit changed by our test function at this point. So in the end, I want to say what I have done here really new, add special for the models. So we have here this AND 2D model, and I can just say this is an old idea. We have here just the Langton's AND, and this is known over years. In addition, we have here tori, and I just noticed there are some paper about twisted tori and Langton's AND telling that we have their kind of unpredictable patterns, which is where I think, well, in other words, that means there's a pseudorandomness. And well, then we have there this convolution idea where convolution is so simple that I think that's not really special. And we have this multicolor idea where I think it's old, like it's the same age like the Langton's AND itself. And then we have, in addition here, my multidimensional AND implementation, while I have here some rules applying on arbitrary multidimensional spaces. So here we can see the first time that we can use Langton's AND in any multidimensional spaces or in any multidimensional tori. And well, that's absolutely new. And I have here in addition the simplified idea which enables us to do it in a simple way. And then we have here this fractal AND colony, while I can just say this is absolutely new. I would think there's no one else on the planet who thinks at the same moment about this idea. And well, then I just have to say thank you that you watched my whole video. You can find several links in the description. And well, have a nice day and goodbye.